Let's look at an example now to see how we can use these equations for our current amplifier. So what we want to do is we want to determine our input and output resistances for a feedback current amplifier. So we know that means it has a shunt series configuration. And for the amplifier, we know it has an open loop gain of A sub I equals 10 to the fifth, a closed loop gain of A sub IF equals 50, an input resistance of 10k ohms, and an output resistance of 20k ohms. So note that these two resistances here, as well as this open loop gain, correspond to sort of just our open loop amplifier. So as we saw in our simplest diagrams, that corresponds to this A sub I. And so of course this A sub IF corresponds to once we've incorporated the feedback with the beta, and ultimately this input and output resistances that we're looking for correspond to once we've implemented our feedback as well. So let's start with our transfer function equation. So we need to start there because the only piece of information we have about our closed loop system is this closed loop gain. So we know in a previous video we found that our closed loop current gain is equal to our open loop current gain divided by 1 plus beta times our open loop current gain. So let me put a beta I there. And so like we saw previously, for an example with our bandwidth extension, the only unknown variable here is our beta sub I, but we don't necessarily need to solve for that explicitly. Instead, we can solve for this whole quantity here in the denominator. The reason for that is because that's the same quantity we're going to be using as we multiply or divide variables to get our input and output resistance. So doing that, what we see is we have our 1 plus beta I times A sub I is equal to our open loop gain divided by our closed loop gain, which is equal to 10 to the fifth divided by 50, which is equal to 2,000. Okay, so now we have that value. So what we want to do is we go back to our equations for our input and our output resistance. So we say our input resistance for this whole feedback network is going to be equal to our input resistance of our open loop amplifier divided by this 1 plus beta I times A sub I value. So plugging in, we know that our R sub I was given as 10,000 ohms, 10K, and we're dividing that by this quantity of 2,000. So note, I've gone back to using sort of base units in ohms as opposed to leaving that in K. And so we could have done that either way. If we left it 10K, our answer would be in kilo ohms. But in this case, we see it's going to make more sense because we get a value of only 5. So we have 5 ohms for our input resistance to that feedback amplifier. So our output resistance for that feedback amplifier, R sub OF, is equal to 1 plus beta I times A sub I times the output resistance R naught of our amplifier, sort of our basic amplifier with no feedback connected to this configuration here. Plugging in values, we know that this is going to be 2,000 times our output resistance was 20k ohms. So again, you can either leave that as 20k or you can put it in ohms, whatever you're more comfortable with. And so this actually gives us 40 times 10 to the 6, which I can just write as 40 mega ohms. So as advertised, we see that for our current amplifier configuration, our shunt series, that our input resistance is drastically decreased when we employ feedback, and our output resistance is drastically increased. So let's take a closer look at that equivalent circuit and again just kind of note how that is behaving how we want it to. So for both our input and output sides, let's consider current division. So on the input side, the current that we're interested in is going to be that AI prime, so sort of going into the amplifier, which is represented in sort of this green here. And so our AI prime we know is equal to the input current, I sub I, times, now we know we have the sum of the resistors in the denominator, so RS plus RIF, and for current division we put the opposite resistor in the numerator, so RS. And so in this case, we can see that if we have a small input resistance to our feedback amplifier, small r sub if, what that means is our output, or our input to the amplifier, I should say, our I sub I primed, is going to be closer to that input, closer to our I sub I. And so that's a desirable thing because we don't want to be losing our signal in this resistor RS here. Okay, so that's good. That is what we wanted. Let's verify that that is also true for our output. So for our output, we can say our output current in our load, I out, is equal to A sub IF times I prime. So basically that's this value here coming out of that dependent source. And then we have a current divider between our RL and our R naught, or our R naught F. So we have the combination of the two in the denominator and the opposite resistor in the numerator. So if we're looking at current in R sub L, we put R sub OF in the numerator. And so what we see here is, remember, we had a large R sub OF. And so what that means is that this output current is going to be closer to the value coming out of this dependent source. But another way to interpret that is we can say that IO, or our output current, is going to have less dependence on our output resistance, which in general is going to be a desirable thing. So hopefully you have a better idea now of how to use these equations in order to analyze these two ideal feedback topologies.